Okay, complete the table using the calculations from the investigation on the previous page. You know what? I'll just do it with the discriminant, that way I don't need to look at the previous page. B squared minus 4ac here would be minus 6 squared, which is 36, minus 4 times 1 times 5, meaning 20, so it's 16. Here, b squared is 36, minus 4 times 1 times 9 is 4 times 9, 36, so 0. And for the last one, minus 6 squared is 36, and then minus 4 times 1 times 13 is 52, so we get minus 16. What does that do to the roots? Well, in the case where this was positive, where the discriminant, we call it, comes out positive, you get two different roots. You get a curve that comes down like this. Remember, the roots are places where it hits the x-axis. In this case, your curve goes through the x-axis and then comes up in a different spot through the x-axis again. If x is 0, or sorry, if the discriminant is 0, then instead you get a curve that comes down, just barely makes contact with the x-axis in one spot, and then turns away again. And if the discriminant is negative, then you have the case of a curve which never makes it to the x-axis. Doesn't touch at all. So, this first case we had two roots, and we call them distinct roots to indicate that they're different numbers. This could be like minus 2 and 2. They could be 5 and 50. They could be 6 and 7, but they're two different numbers always. In this case, let's say there's one root, and it's what we call a repeated root. If you try to factor this, you'll find what you get is x minus 3, x minus 3. If you solve each of those, you'll get 3 here, and then you'll get 3 again. So we say it's a repeated root because when you're solving the equation, you end up getting the same number more than once. Some people, instead of 1 and repeated, put here that there are 2 roots and that they're equal, which I don't agree with. I don't think it's accurate to say that you've got 2 roots when you've got the same number happening repeatedly. But if your teacher wants you to go with that, then okay, you can live with it. My preferred expression is there's one root and it happens more than one time. And the last thing that can happen is, in this case, there are no roots, so we say no roots. The truth is, there are roots, but it takes complex numbers, as in the square roots of negative numbers, to solve for them. So in this case, you could say that the roots are complex, or the other thing that they say is that the roots are non-real, meaning they're not part of the real numbers. For these other cases, you could say the roots are real and distinct, or here that the roots are real and repeated. These roots are not real. There is a way to find them. We'll show you much later, but for now, we basically, most of the time, we treat these equations like they don't have any roots. So, to summarize that, if the discriminant is exactly 0, then the roots are real and repeated. If the discriminant is greater than 0, meaning it's positive, then the roots are real and distinct. You know what, I'll put equal next to this first one just in case that's what they want. And the last possibility is the discriminant is less than 0, in which case the roots are complex. Or, if you prefer, the roots are non-real.